Okay, so last section for this week is 7.4. Okay, a little bit different than the other sections we've done because there's nothing numeric in this section. This is all on trig identities. So big idea is, I'll just show you a sample problem. You're going to be giving something like that, and you have to simplify it as much as you can. Okay? I'm going to remind you of the different equations you can use to simplify that right now. Okay, so just as a reminder, what is an identity? An identity is an equation that is always true. A squared plus b squared equals c squared. That's an identity. It's an equation that is always true if you're dealing with a right triangle. Doesn't matter what the specific legs are. One leg squared plus the other leg squared always equals the hypotenuse squared in a right triangle. There's no exception to that. Okay? In Algebra 1, here's what an identity would look like. If I gave that as a problem in Algebra 1 and said to solve, well, when you start to solve it and you distribute, you get 2x plus 2 plus 3. Plus 2 plus 3 is plus 5. You get 2x plus 5 on the left, 2x plus 5 on the right. Whenever you end up with the same thing on the left and the right, basically, you subtract 2x from each side and then it's gone. You're left with 5 equals 5. So in Algebra 1, somebody would write the solution to that as all real numbers. You can plug any number you want in, and it works. Okay. Compared to something like this, that is not an identity. That's a conditional equation. It's true if you pick the right value for x, but only if you pick the right one. In a problem like this, you can't pick the wrong one. Anything you pick will work, because it's an identity. So we're going to look at equations like that, but they're not going to be algebraic identities. They're going to be trig identities. Okay, you should already be familiar with the tangent, the cotangent, the reciprocal, and the Pythagorean identities. Okay, these are already in your notes. If you want to put them again, go ahead. A lot of them we use all the time, so you just kind of have to remember them. Like these three. If you want to type cosecant in on the graphing calculator, there's no button for it. You have to take 1 over the sine. Okay, secant, 1 over cosine, cotangent, 1 over tangent. And the ones directly above them are really repeats. These aren't 6 different identities. Okay. Those two are exactly the same thing. If you say that what's in that red box is 2 different identities, then that's like saying that's 2 different formulas. No, I argue they're the same formula. You just took and you just moved the letters around. Okay? Same thing if you did this. Distance equals rate times time. Distance divided by rate equals time. Distance divided by time equals rate. It's the same formula. You're just moving stuff around. That's what's happening in those two. You're just moving stuff around. Okay? Same with these two and the next two. Any question on the reciprocal identities? Question? No? Okay, so we've got those. We've got the quotient identities, which say that if you take sine and divide by cosine, you get the tangent. And if you flip it, cosine divided by sine is the cotangent. Okay, so those will come in handy. And then the last group, when I taught you these, I said just write them down. We're not going to do anything with them on the test because I wanted you to have them all in the same spot. Well, if you're copying them all down again right now, that didn't really matter. But the Pythagorean identities are right here. Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And then 1 plus cotangent squared equals cosecant squared. So using these identities, basically what we're going to do is substitution. You're going to plug one thing in for another, and we're going to hope that by doing that we get stuff that cancels out. Now, looking at all those formulas, does anybody see a trig function that comes up a lot? It's a trig function that you can actually just use these two to write every trig function you'd want to write. Yeah?
Sine and cosine.
Yeah, you can do everything in trig with just sine and cosine. You can write tangent with sine and cosine. You can write cotangent with sine and cosine. You can write secant just using cosine. And you can write cosecant just using sine. And then sine is itself and cosine is itself. So sine and cosine are the only two trig functions you really need to do everything. All right. So the reason we work with trig identities, we're never really going to be doing the like a word problem or an application part. But the idea is that in calculus, if you had something that was really complicated to work with, maybe like this. If I had to do something with that in calculus, it's kind of a pain. It's a fraction, and there's two different things. Well, maybe I can get rid of that fraction, and I could make it just one thing instead of two. If I could do that, it would be easier to work with for whatever I have to do in calculus. All right. So we're never really going to be taking it to the next step, which is now that you've done the part we're going to do, now do the calculus part. We don't do the calculus part. So we just simplify it, and then we just stop. We don't do anything else with it. So since sine and cosine are the two most important trig functions, basically one trick to simplify a trig identity is to change everything into sines and cosines. And I just showed you earlier that that can be done. I circled all the formulas you could use. And the hope is that when you change everything into sines and cosines, somehow something cancels out. Okay, every problem that I give you has been made so that it will work out nicely. Okay, trig identities are not always the easiest to figure out. I think when I do them up here, I can kind of lead you in the right direction and make it look easy. But then when you have to figure it out completely on your own, sometimes it's a little hard to know what to start with. Well, I'm giving you a hint. This might be something you want to start with. Okay. Change to sines and cosines. It's not the only trick, but it is one trick that does help us. Okay. Now, not to complicate it, but like any trick, you don't use it all the time. There are times, not all the time, but sometimes, when changing things to sines and cosines might actually make the problem worse. Okay? I'd say like 90% of the time it's going to help. There's a few times it doesn't. And if you run into one of those times when it doesn't, you're going to start doing the problem, and it's just going to feel like it's getting worse and worse. And then it's at that point, it's like, okay, let's start over and let's try something else. Okay? So usually you can figure out very quickly if changing to sines and cosines was the right thing to do or not. Okay, so let's look at this one. It says cotangent divided by cosecant. And it doesn't matter what the angle is. We're not doing anything numeric today. This formula that we're about to come up with would work for any angle you want to use. You want to let theta equal 10? Fine. It'll work for that. Theta equals 76? It'll work for that. It's just generic. It'll work for anything. So let's start with cotangent. Can somebody tell me how I can rewrite cotangent in terms of sines and cosines?
Cosine over sine.
Yep, cosine over sine. Okay, so that's the top. And how about cosecant? Mina?
1 over sine.
It's 1 over sine. What you have right there, if you wanted to look at that, like with numbers, is very similar to something like this. When you divide two fractions with the same denominator, what happens to the denominator?
Cancel.
It cancels. Some people say, well, you could multiply by the reciprocal. It's the same thing. It would cancel the denominator. So what happens? You're left with that, which is now just cosine divided by 1. But if you divide something by 1, it's just itself. So now we've taken a problem that had two trig functions with a fraction. We made it a single trig function, no fraction. So now if I had to do something with that in calculus, that is going to be a lot easier to work with than the other thing we started with. That's much more simplified. Okay? But for us, that's where we stop. Okay. Any question on that one? Okay, that's an easy one. They're not all that easy. But a lot of them that I'm going to give you on the test will be similar to that. Okay, let's try this one. Okay, cosecant times tangent. Okay, since the only trick we know so far is to change in sines and cosines, I haven't told you anything else yet. Let's try that. Okay. Dave, could you tell me what cosecant would be?
1 over sine.
Yep. It's 1 over sine. Times. And how about tangent? Caitlin.
Is that in the sine?
Yep. It would be sine over cosine. And now when you multiply fractions, you go straight across. So what would cancel out here?
Sine.
Sines. And now you're left with 1 over cosine. And at this point, you might say, well, should I stop there? Is that as much as I should do? I would argue that if you can write a final answer not as a fraction, that's simpler than having a fraction. So I would go one more step with that. What is 1 over cosine? It's secant. So now you've taken a problem that had two trig functions as a product. You made it a single trig function, no operation at all, just secant. It won't all come out that nice, but the first couple will. Okay. Any questions on that? All right. So some directions are going to say simplify. Simplify can be a little confusing because they give you something to start with and you just have to work with it as much as you can until you think you're done. Versus if I give you a problem that says verify. I think verify is easier because they give you something to start with. They give you something to finish with. All you have to do is figure out how to turn that into that. So you know when you're done because they're telling you where to stop. So that's the difference between verify and simplify. Simplify, it's kind of open-ended. You get a problem, do as much as you can until you think you're done. Verify, they're going to give you a problem with an equal sign in it. That doesn't have an equal sign, that's not a verify. That has an equal sign, that's a verify. Okay. And the way you show an identity is true, the way you verify it, is you just make the left and the right-hand side the same. So you just keep working with the complicated side until you're done. And the reason I say start with the complicated side and simplify it is because, I'll come right back to that, it's a lot easier to take something that looks complicated and try to make it simpler than it is to take something that's simple and try to complicate it. That's harder to do. Always take the side that looks more complicated, which I would argue here is the right side, and try to simplify the right-hand side. I'm just showing you another one. Here, in terms of which side looks more complicated, I would say they both look the same. I don't really think the left side or the right side is more complicated than the other. But here it's very clear. The left-hand side is much simpler than the right. Okay, another approach is you can try to work with both sides at the same time, but that usually confuses people. So we're just going to stick with that. Okay, any questions on that? Okay, so our first trick with trig identities was to change everything into sines and cosines. Okay. Second trick is if you have fractions with different denominators, try writing it with a common denominator. So once you know this second trick, now you have to decide when you should use it. Well, if you're finding a common denominator, that means you have a problem with two fractions, like this. If you wanted to do that, you need a common denominator. Well, if you look back at this problem, there's no denominators in this problem at all. You're not adding two separate fractions together. That's why you would never use that trick here. Here you're dividing two fractions, but it's just a single fraction. You don't have two separate ones being added. So you wouldn't use the common denominator trick here either. I'll find one eventually where you have to do that. I think I have one under the slide. The second trick, write with a common denominator. All right, so would this be a problem the way it looks right now, where you should be thinking about common denominators right away? No, there are no denominators. They're all one. Okay, right now. Maybe common denominators will come up later in the problem, but not now. Okay, so you have two choices of things you could do first here. You could change everything to sines and cosines. Or, what other property do you think you could use here that we use all the time with numbers like this? Think about just the structure of that problem and pretend that those were numbers and letters, not trig functions. Distributive? Distributive, yeah. So at some point, you're going to have to do both. You're going to have to do distributive, and you're going to have to change to sines and cosines. Which one you want to do first is up to you. Okay, I'm going to do the distributive first. So we've got sine times cotangent plus sine times tangent. Okay, so there's our distributive. Questions on that? Okay, Ezekiel, now what do you think I'm going to do with everything that's there? Yeah, we're going to change everything that's not a sine and cosine into one and hope we get some stuff that cancels. So we've got sine times cotangent.
Cosine over sine.
Cosine over sine. If you want, since we're making everything fractions, you could make sine a fraction just by putting it over 1. That's up to you. Sine is already sine is already sine, so don't change it. What about tangent?
Sine over cosine.
Sine over cosine. Now, you cannot cancel across a plus sign. If you had something like this, you absolutely cannot do that and just say the answer is 3/8. Then why do we teach common denominators when add fractions if that just worked? Okay? You can't cancel across a plus sign. What you can do is if you had something like this, and the plus sign wasn't there and it was multiplication, Absolutely. Now you can cancel. Okay. So if you're thinking, well, I'm going to cancel the sign in the bottom here with that one, no. That's across a plus sign. So is there anything that's separated by a multiplication that we could cancel? Yep.
2 signs.
Yep, that's perfectly fine. But that's the only thing that cancels. So we're left with cosine over 1. Plus, now we have sine times sine. Sine squared. Don't mix it up with 2 sine. Think of x plus x versus x times x. Okay. Sine times sine, sine squared. And then in the bottom, 1 times cosine is cosine. So now, when I see a sine squared, I'm not there yet, but what I'm starting to think of in my head already is this. I'm starting to think that that might come up somewhere, because now I see sine squared in the bottom. Okay, so keep that in mind. All right, so let's go back. Okay, so now we've changed everything to sine and cosine. We're done now. What could I do with this now? Can you cancel cosine? Right, because that's across a plus sign, but what we can do is find a common denominator. We have a 1 and a cosine. Yeah. Easiest way to find a common denominator, just take the 2 that you have, multiply them together, that's the common denominator. So we're going to write everything with a cosine. Is there any fraction here that already has a denominator of cosine?
Yeah,
the right one, so you can leave it. You don't have to change the right fraction at all. The left fraction we do. What would you multiply top and bottom by to turn this denominator into cosine? Cosine. If you multiply in the bottom, you got to do it in the top. Now, cosine times 1, there's your cosine. What's cosine times cosine? Cosine squared. So now in the top, we've got cosine squared plus sine squared. Let's go back and look at this. This says sine squared plus cosine squared. But is that the same if you switch the order, you add 2 things in? Yeah, like if you do 2 plus 5, 5 plus 2, the order you add doesn't matter. So what's cosine squared plus sine squared equal to? 1. So that entire numerator that we have, all of this turns into 1. And now, again, the argument I think we could make is you can go one more step and get rid of that fraction, and you're done. Secant. So we took what was a really complicated looking problem that had 3 different trig functions. It had distributive property, addition, it had parentheses. We simplified everything to a single function, secant. So doing what I have circled, if you would plug that in on your calculator, and you were to plug in a number for all this stuff, you'd get exactly the same thing. That's a much, much simpler way to do it. Okay, so that's more of that's like a medium one. That's not as easy as the first one, so that's a little harder. Okay, any questions on that one? Okay, so our first verify. So again, I like verify because I know what I'm supposed to get for the answer. There's the answer right there. All we have to do is play with the right-hand side until we get the left. Okay, first I should probably ask the question, does everyone agree that the right-hand side is more complicated than the left? Okay. You should always start with the more complicated side. Okay, so I'm going to write it down so then I can start doing stuff to it. Okay, at this point, we wouldn't be finding a common denominator because you only have one fraction in the whole problem. Common denominator means you have two separate fractions. So we don't have to worry about that at this point. What else could we try? Besides finding a common denominator. Yeah?
Turn tangent and cotangent into sine and cosine.
Yeah, let's change everything into sines and cosines and then see where we go from there. So secant is 1 over cosine. Tangent is sine over cosine. And cotangent is cosine over sine. Now, can we just cancel everything? Cancel all the cosines and the sines? No. It's across a plus sign. You can't do that. If it was multiplication, yes. All right, so there's not really a lot we can do in the top. Let's look at the bottom as kind of its own separate thing. We have two fractions. Okay. What could we do with each of these fractions now? What's the other trick we learned? Common denominator. So I'm just going to keep the top the same till the very end of the problem. Just keep copying that down. So the only thing we're really doing is playing with this bottom part right there. Okay, what's the common denominator of what's in that box? Well, that's like if you had 2 over 3 plus 5 over 7. You can't say 3 or 7 is the common denominator. It would be 21 here. So here it would be what?
Cosine sine.
Cosine sine. You have to take the product of the two that you have. Okay? Cosine sine. Okay. What is the fraction on the left missing to make it have the common denominator? The fraction on the left has the cosine in the bottom. It's missing the sine. So you're going to multiply by sine over sine. What's the fraction on the right missing? It's missing cosine. You always multiply each fraction by the other denominator. That's exactly how you would do it here. You multiply by 3 over 3, comes from that denominator, and 7 over 7 comes from that denominator. And then your common denominator now is, in this case, it's a number. In this case, it's an expression. Okay, sine times sine gives me
1.
We're going to get there, but not yet.
Sine squared.
Sine squared plus cosine times cosine? Cosine squared. And now, all of the stuff I just pointed an arrow to, what does that all turn into? That's all turning into a 1. So you're left with 1 over cosine sine. Okay, now there's a couple ways we can do it, but when you divide two fractions like this, how do you divide two fractions?
Multiply them by the reciprocal.
Yeah, take the one in the bottom, flip it, and multiply by the reciprocal. What about the one in the top? Just keep it the same. Take the one in the bottom, flip it, and multiply by the reciprocal. Now we have a multiplication sign separating these two fractions. If there's something in the top and bottom that's the same, can we cancel it?
Yes.
Yeah. Is there anything there we can cancel? Cosine. Cosine? Cosine. So all you're left with is sine, which is exactly what we were supposed to get. So the way I did that, that's not the only way to do it. Okay? Most of the identities I give you, you can probably do in under 6 or so steps. If you start getting into a problem where it's taking like 9, 10, 12 steps, there was probably an easier way. But that's the thing with trig identities. There's many, many, many different ways to do it. I would argue that's probably the simplest way, but I could be wrong. But I think it's the simplest. Okay. Any questions on that one? So that's more of a medium hard, okay? Because it's got a lot of stuff in it. It had change to sines and cosines, find a common denominator, a Pythagorean identity, and then multiplying by the reciprocal, and then canceling some stuff out. So there was a lot in them. Okay, so the last trick that I'm going to teach you to simplify identities is to multiply the top and the bottom of an identity by a conjugate. Now, you're going to know when you have to use a conjugate. It's a very obvious type of problem. So the conjugate, if you remember when we studied imaginary numbers, if you had 2 plus I, the conjugate is 2 minus I. We're not doing anything with imaginaries. I'm just showing you another place that we've used the conjugate before. Okay? With a trig function, if you had tangent plus 1, what do you think the conjugate would be?
Tangent minus 1.
It would be tangent minus 1. So the reason I say it's very obvious when you have to use a conjugate is because you always have a trig function plus or minus a number. You do not have that here. That's a trig function plus a trig function. Okay. That's a trig function plus a trig function. So you don't have it there. Conjugate. Trig function plus a number. This is a problem where you would use a conjugate. Okay. So always look for a trig function plus or minus a number. That's the only time you can use conjugates. Okay. Right, so verify. I kind of gave you my opinion earlier, but which side looks more complicated here? Neither one. Okay, they both have a denominator that's just a single term, like a cosine and a cosine. And then they both have a numerator or denominator that's a trig function plus or minus a number. So you can start with either side. Do we want to start with the left or the right? Left. Okay, so our goal is to take that, and when we're done, get what's on the right. Okay, so let's start with what's on the left. Let's run through all the tricks in the order we learned them. Could I change everything here to sines and cosines?
It's already.
It already is, so you can't do that. Maybe that'll come up later, but it's not going to come up now. Could I write this with a common denominator? No. You have one fraction. It already has a common denominator. Okay. So the only trick left is to multiply by the conjugate. Okay. What's the conjugate of 1 minus sine?
1 plus sine.
1 plus sine. Okay, the conjugate, all you do is change the term in the middle. Okay. So 1 plus sine, 1 plus sine. Okay. Now, does anybody play chess? Play chess? No?
I know how to play it.
You know how to play it?
I'm bad at it.
You're bad at it? How come? What do you have to be good at chess? What do you have to be able to do?
Or like know what the other person is doing.
Right. You have to be able to think what's going to happen 2 or 3 steps from now. That's a hard thing to do sometimes. That's what I'm thinking in this problem. In the top, you might be like, well, should I distribute out that cosine? That's what we did before. And the answer here is no. The reason why is because looking at this pattern, I've seen this kind of pattern a lot in like hundreds of problems. I already know what's going to happen 2 steps from now. That's a hard thing to try to teach someone. Okay, how do you know what's going to happen 2 or 3 steps from now? The same way you would in chess. You've played it a lot. You can kind of predict what's going to happen. There's nothing you can just memorize real quick and know what's going to happen. It's practice. So leave the top the way it is. Leave it as cosine times 1 plus sine. Now, if you accidentally did that out, it's not like you're wrong. You're going to make more work for yourself. And by making more work, you're probably going to mess something up. So just leave it just like that. The bottom, though, do that out. Okay? Anytime you have conjugates, there's going to be a lot of stuff that cancels out. Yep. So when we FOIL out the bottom, their conjugates, stuff is going to cancel. Start, what's 1 times 1? 1. Okay. We have 1 times positive sign, 1 times negative sign. What happens there? That cancels. That's why we're FOILing it. 1 times positive sign, 1 times negative sign. Last thing. Negative times positive. What kind of number? Negative sine times sine. Sine squared. Sorry, I should stick with using the same letter. If you use theta, that's fine. If you use t, that's fine, but just stick with the same thing. It doesn't change how we've done anything, but it just looks a little messy to use different letters.
Is it squared?
Squared, yep. Okay, now 1 minus sine squared. Okay, let's go back and look. Actually, I'm just going to write it. 1 minus sine squared is that. What would you have to do to what I just wrote to make 1 minus sine squared by itself on one side? It's kind of like if I said, if I go back to what I wrote earlier. This compared to that. Same thing. All you've done is you've rearranged where you put stuff. Okay? So what I want to do is look at what I just wrote in red, and I want to rearrange where I put stuff. I want to rearrange it so it looks like 1 minus sine squared. So what would I have to do that? Well, there's a 1 and a sine squared there, right? They're just on different sides. So put them on the same side. Yeah, just take and put that over there. Subtract it. If you bring it to the other side, you have this. Is that a new identity? No. It's the same identity, just move stuff around. So any of those identities that I gave you on the other page, you can move stuff around. Okay? So it says here that 1 minus sine squared equals what? Cosine squared. So let's write that in. Okay, so change the bottom to cosine squared.
Wait, what? Oh, that's complicated. That's complicated.
Mm-hmm. It takes a little getting used to.
Oh my gosh. Okay.
Any question on how this is exactly the same as that? The way I proved that is I used our Pythagorean identity. Okay. Sine squared plus cosine squared equals 1. bring the sine squared to the other side, and you've just rearranged the identity a little bit. And 1 minus sine squared is cosine squared. Now, hopefully you can see why I left the cosine here, because it's going to cancel. Had I distributed it out, it would have been a waste of time because it's going to cancel. How many cosines do I have in the top?
2.
In the top?
Oh, 1.
Right here is just 1. How many in the bottom? I have 2. So I can cancel 1 from the top, 1 from the bottom. They both have 1 in common. What am I left with in the top?
1 cosine.
What am I left with in the bottom? That's exactly what I was supposed to do. Okay, so the first time through a problem like that, I think it's definitely a little tricky. But once you see this kind of problem again, it's the same thing every time. Multiply by the conjugate, distribute out the bottom, don't do the top, and then use a Pythagorean identity, and something cancels, and you're done. Okay. The pattern will never change. You just have to get used to the pattern and practice it until you understand it. Okay. Any questions on that one? So these might be good ones to go back, maybe not the first two, because those were easier, but some of the later ones, and just watch it again, because it's not the kind of thing that sinks in the first time. That's why tomorrow is a review day, because I figured we would need that.
Thank you.
You're welcome.
Means a lot.
All right, let's do something a little different. So this says use a graphing calculator. In fact, I'm not even going to do it. I'm just going to ask you how you do it. Now, a graphing calculator can't prove anything, right? All the stuff we've been doing, you can't substitute a graphing calculator for doing this algebra. But you can use a graphing calculator to support an idea. Not prove an idea, but to kind of say, this is what I think should happen. How could you use a graphing calculator to support that what's on the left is equal to what's on the right?
Put it into Y1 and Y2.
Okay, put that into Y1, put that into Y2, and then what would you look for?
If the lines are the same.
You'd look for the facts, see if they're the same. So, if Y1 appears, I'm not going to say is equal to, because we can't really tell exactly. Maybe you zoom in and it's a little off, we don't know. But if Y1 appears to equal Y2, that suggests, be very careful with the word I used, it does not prove anything, but it does suggest that what's on the left and what's on the right are the same. So it suggests that the left-hand side, that's LHS, equals the right-hand side. The only way to actually prove it is to do what we've been doing. Okay, so I'm just showing you can use a graphing calculator to kind of test an idea. And that's, if you were given an identity or given a problem randomly, I would always graph it first. Because why am I going to waste time trying to prove two things are equal if they aren't? Okay? If they look different on the calculator, then I can see that very, very quickly and not waste my time trying to show they're equal. Because in calculus, when you really do like trig identities, they don't just say verify. They say verify if possible. So what that means is maybe what I'm giving you works, maybe it doesn't. You have to figure out if it even works first. And then if it looks like it could be true on a calculator, then go ahead and use the algebra and try to prove it. If it looks like they're totally different and they don't have anything in common, don't waste your time. Don't bother trying to prove it. Okay. Any questions on that one? Okay, so I've pretty much shown you all the different tricks. Yeah, you just need to practice it. I have a couple other ones. Does anyone want to see another one, or just practice?
I'm sorry.
All right, let's try this one. It says tangent squared minus 1 over secant squared equals, and the right-hand side is tangent x minus cotangent x, and the bottom is tangent x plus cotangent x. Okay, I would say start with the right-hand side. I think that looks a little more complicated because there's 4 things there. There's only really 3 things on the left. So, but you could probably argue either way. Okay. What could I try first on the right-hand side? I could change everything to sines and cosines. That might work. What else could I try? Another trick that we learned.
Multiply top and bottom.
Yeah, we've got something plus something. Now, it's not something plus a number. So we could try the conjugate. I honestly don't know if the conjugate's going to work. We try it. We'll see. If it looks like it's going in a good direction, we'll go with it. If we try it and it looks awful, then we'll just stop and we won't keep doing it. Okay.
Wait, shouldn't we just put it all into sine and cosine then?
Well, that's another option.
Oh yeah, let's just do that.
I think that it would be easier to do it that way.
No? I don't know.
I'm not 100% sure, but I think we should try the conjugate. But I could be wrong. I don't know. You can't memorize every identity, and I don't know how this one works out. So I have no idea how to do it when I ask you how to do it at the moment. But I will. I'll figure it out as we go. So I think the reason I like the conjugate is because I just see top and bottom. They look very similar, and I think the conjugate is going to cancel stuff out. So let's try. So let's take tangent x minus cotangent x, tangent x plus cotangent x. And we're going to multiply top and bottom by the conjugate. Okay, so let's multiply top and bottom by the conjugate. You could pick the conjugate of either one. Let's do the conjugate of the top. Tangent plus cotangent. And do the same on the bottom. Now the top, I know some nice stuff is going to happen because they're conjugates. What's tangent times tangent? Tangent squared. Now, before I go any further, just to kind of tell you like what I think about as I'm doing this, I see tangent squared. Okay, in my head, I'm already starting to think about this. I see tangent squared. I know there's an identity with tangent squared. I'm hoping that that comes up somewhere. If I don't start to see this identity pretty quick, then I know what I'm doing, not a good approach. And then maybe sines and cosines would have been better. Okay, let's go back. All right, so tangent squared. Tangent times positive cotangent. Tangent times negative cotangent. What happens there? They cancel. Negative times positive is a negative. And what's cotangent times cotangent?
Cotangent squared.
Cotangent squared. Okay. Any question on the top? Now, tangent squared minus cotangent squared. I'm going to go back. I'm going to go look at the identity again and see if something is there. So keep in mind what it was. Tangent squared minus cotangent squared.
Nope.
Yeah, that's not good. So we have tangent squared and cotangent squared, but they are in different identities. So I don't particularly like that. So at this point, I would look at it again. Wherever it is. And this is how solving identities normally goes. All the other ones, I kind of already knew what to do. This one, I don't. So this is normally what happens. You try something, and then you look at it.
Happening to us on the test.
Is it going to happen to you?
Yeah, on the test.
Something like this.
Please say no.
Well, similar to ones like this. Not exactly like this.
It's only been about 3 weeks.
If you don't know what you're doing.
Oh, I'll show you how to solve it. I don't know if I'll do it today, but I will show you. Probably tomorrow. So, I think changing to sines and cosines, that might be a better way to go. And again, this way might not be wrong either. There might be more you could do with this. Maybe I'm just not seeing it quickly. Maybe we are on the right track and then I'm just like one step away, but I'm just not seeing it because I don't see everything right away. Yeah?
Did you turn the numerator from the left side to negative secant squared?
This?
No, on like the original problem.
The original?
Yeah, can you turn the numerator into negative secant squared?
The numerator, tangent squared minus 1. Let me go back and look at the identity.
Yeah.
That might have been, let's see. So,
Just move it to the other side.
yes, we do have tangent squared and 1 in the same identity. So, what do we have? Tangent squared minus 1?
Yeah. Oh.
No, it's got to be plus 1. That won't work. If it was a tangent squared with a plus 1, that would have been good. We've got a minus 1. I'll think more about it. Hey, that's a hard one. It's probably the hardest one I had today. But I will think more about it, and maybe I'll just pause the video and I'll do it out, or you guys start the homework. I'll figure it out.
Is there going to be something like this on the homework tonight?
I don't know if there's any. If there is, there'd probably be one, but a lot of them are easier than this.
All right.
Yeah. Okay, I'll finish that one up. Okay, so the homework, it's not a ton of questions. Some of them are very easy to start out with. There are a couple towards the end that get a little harder. Okay, but it's 407, 4 through 8, 11, 12, 21, 22, 25, and 27. Okay, what I would do now is just take a look at it, read the directions for each problem. If you don't understand the directions, ask me what they mean right now, and I'll tell you.